Welcome to ExplainerCast episode 21. I'm your host, Dave Smith.
And this is Shane Swenson.
ExplainerCast is a podcast where we have some explaining to do.
Yep.
And today we're going to explain scaling laws.
Yes. And these have been showing up in the news lately, Dave. Where have you seen this?
In a context that has a lot of hype and therefore so unsurprisingly misplaced use of terminology, This has shown up in the world of generative AI, where the context of scaling laws is how big does our data set need to be? Does our compute cluster need to be? Does our network bandwidth need to be in order to produce the next generation of awesome generative artificial intelligence?
And the answer is, of course, always a lot bigger, right?
Yes, much bigger. And about 80% of the people say it won't help, and then 20% of the people say it will, and I'm following scaling laws.
And so far, who's been right?
The 20%. That's the crazy part. But Shane and I are very disappointed in the use of the word laws here because there doesn't seem to be any kind of underpinnings to the word. It just seems to be like maybe scaling hope or scaling observations would be a better way to put it.
Yeah, I was going to charitably call them observations, but they do seem to be a little bit aspirational, so maybe hope is right. But yeah, they so far the data points have trended in the direction needed enough for people to kind of conclude that maybe there is some substance to it. The challenge with these things is in the short run, it can be true. The question will be how far maybe do they go before they hit some unmodeled constraint that essentially shuts the increase down.
And I want to call out before we get too far that these are not the laws we're going to talk about today because we don't think these are actual scaling laws.
That's right.
But before we go to the real scaling laws, there is another very popular law that has been applied to scaling. I don't know if you could hear in the inflection in my voice, but I put the word law in scare quotes when I said that.
I definitely heard it. Yeah.
Okay, good. And that is Moore's law, the so-called Moore's law, which we did an episode that covered Moore's law.
Yep.
I can't remember the episode number. You'll have to.
As early on.
Yeah. This, of course, was also not a law. I tend to think of it more as a prophecy or maybe a project plan.
Sure.
that,
which did
everyone
come true.
marched to. Yes. It was one of the few project plans in software and hardware that actually came to fruition, but also not a law and also not what we're going to talk about today.
That's right. But yeah, that one was interesting because it did, and yeah, it was episode 4. I just looked it up, but it did allow the entire semiconductor industry to essentially coordinate on how fast were they going to make progress. And it started as an observation. So again, you could have called it Gordon Moore's observation, but it was named a law. And then I guess people felt compelled to follow the law and to keep it going for decade after decade. And it really probably actually was a bit of a self-fulfilling prophecy because it set the cadence for the rate of improvements in semiconductor technology needed to achieve the scale that the law would predict. And so it kind of told all the manufacturers and chip designers what they needed to build next and when they needed to have it ready by. And that probably actually is why it was successful. Perhaps without it, we would have had a different outcome.
Yeah, I have to imagine that semiconductor progress, and frankly, maybe all of compute progress, could have gone a lot slower were it not for this schedule that was foretold by the great prophet Gordon Moore.
Yeah.
And not only is it just a schedule that people feel compelled to work toward, but it actually gave people the ability to line up timelines. Like Shane is surprisingly familiar, maybe even suspiciously familiar with the CPU supply chain and all the intricacies involved there, to the degree that if you were planning that yourself, there would definitely have been inefficiencies introduced if all of these components weren't already working together to hit the next 18-month to 2-year mark for the next doubling of performance.
Right, exactly. And because it was a multi-company, multinational endeavor, that level of coordination was essential because you wouldn't want to spend all the money to build something and not be able to use it. But yet there's a huge amount of work needed to make use of those new technologies in terms of updating your designs and so forth. So it really is quite remarkable that we're here now as opposed to sort of somewhere maybe less progressed on the technology timeline at this point in time.
And it would have been substantial because we've had, I don't know what, like 20 iterations of Moore's Law now?
Yeah, I mean, since the 1960s. So yeah, maybe 30.
Yeah, maybe even 30. And, you know, as interest rates go, because this is kind of a compounding interest problem, right? If the period that Moore had observed and declared as law, or was declared by others, if it had not been 18 months or 2 years, if it had instead been 3 years, we would definitely not be anywhere near 30 iterations.
Yeah. Yeah. So if you had 20 doublings instead of 30 doublings, like that's a huge difference. That's a factor of 1,000.
Yeah. We would be using like Palm Pilots today.
Yeah.
Instead of the
and thinking they were really cool.
Yeah, exactly. We'd be like, wow, we are advancing so fast.
Yeah. Can you believe it? This exponential growth.
I mean, there's exponential and then there's exponential.
That's right.
Like the coefficients are important. Okay. Well, should we get to the actual scaling laws with a capital L and no scare quotes around them?
Yeah. Let's do something that's a little more down to earth. And we're going to talk about, something much more basic and maybe a little bit easier to observe with our own eyes and understand. So, so what do we mean by scaling laws for the purpose of the rest of this conversation, Dave?
Well, this is going to be in the context of physics. And one of my favorite quotes about physics is the law, everything else is a recommendation. and this is what we're going to go into because it turns out, and I know we're going to talk about this on multiple dimensions, but one of the dimensions we're going to talk about is size.
Yeah.
Which is like objects cannot get bigger following a certain formula and still maintain some of the same properties. They have to shed properties or change properties as they get bigger.
Yes.
And the same thing is true of smaller, right? Like when you go up or down in size, and there's a lot of ways to talk about size. So Shane, I'll just hand it over to you because I just hit the limit of my understanding.
Yeah. and sadly, I already have to put a caveat, which is I think sadly, even in physics, we're doing our best to explain something through observation. Like none of us actually know the true fundamentals of how our physical world works. So we go with, I think one of the kind of standards is you go with the simplest possible explanation that adequately describes your data and predicts future results. And we're going to ignore some corners, like we're not going to go into quantum, we're not going to go into subatomic forces, things like that. We're going to talk about what we might call Newtonian mechanics, like kind of those described by Isaac Newton, and sort of real world object scale that we humans interact with the world in. And so, for example, when you watch like an old movie, you know how you can just tell when they were using a small scale model to represent something like King Kong or something like that climbing the Empire State Building, and you can just tell like, oh, this is not actually a huge animal. It just doesn't move right. You can sort of tell the difference. Have you noticed that?
Yes. The key is in the motion. Like something that big can't swing its arm that fast.
Yes, exactly. And by the end of today's episode, I'm hoping it'll be understandable why that is true. Another example would be we love to extol the virtues of the small but mighty. So think about ants carrying multiple times their body weight, or grasshoppers jumping multiple times their height or distance. And why can't we humans perform at the level they can perform at?
I know. Well, I'm going to say in a word, scaling laws.
Scaling laws. That's right. Okay, so let's get into it. And really this all comes down to a fairly basic principle. And the basic principle is that what we call the size of something, and we're going to specifically talk about what we would call a linear measure of size. So the length or the height or the width of something. As we increase that, the object itself grows in mass at a much faster rate. So if we took, say, I'm trying to think of like what would be a good example object to work with in our minds here.
So you're looking for something that can grow
something
at
simple.
One rate, like a soccer ball.
Yeah, a ball is a great example. And let's start with a solid ball, like a rubber bouncy ball that's like solid all the way through.
Okay.
And let's say that it's an inch in diameter. And if we were to double it so that it's 2 inches in diameter, what's going to happen to the mass? Is the mass going to double?
No, the mass is going to more than double.
The mass is going to more than double. And in fact, the mass is going to increase by a factor of 8. And maybe an even simpler object to think about would be if we took a cube. Let's say we took like a block of wood, a 1-inch cube. It's 1 inch on each side. And we were to make it doubled in length and width and height so that it's 2 inches on each side. When it was a 1 inch by 1 inch by 1 inch cube, the volume is 1 times 1 times 1 is 1 cubic centimeter. When we double each of those linear dimensions and it becomes 2 by 2 by 2, 2 times 2 times 2 is 8. And it becomes 8 times the volume, which means it is 8 times the mass. So
Mm-hmm.
it just got way heavier. In fact, so we doubled the length, we multiplied the mass by 8, which means we actually quadrupled the ratio of mass to size. And this is where the scaling kicks in, because that 1-inch cube is going to have any property that's dependent on the mass when you go to the 2-inch cube is going to go up by 8x. But if there's a property of its behavior that is associated with the length, that's only going to go up by 2x. And the difference is where we see this.
Yes.
Another property that's very important is if we look at the cross-sectional area of that cube, or say the area of one of its faces, the 1-inch cube, its area is a square and it's 1 inch by 1 inch. So that's 1 square inch. If you look at the cube that we doubled in size, it's a 2 inch by 2 inch face. So that is 4 square inches.
Yes.
So we doubled the length, we quadrupled the surface area, and it turns out this is true for all 6 faces. So the total surface area is also increased by a factor of 4. And we multiplied the volume or the mass by 8. So any property that's associated with the length doubled, properties associated with surface area quadrupled, and properties associated with mass went up by a factor of 8. So if you look at, say, that King Kong example, first of all, it's going to be extremely heavy because it's huge, and mass went up again at 8x every time it doubled. Meanwhile, how much strength does it have? The strength of your muscle is roughly proportional to the cross-sectional area of the muscle. So if you doubled the size of an animal, its mass goes up by 8, its strength really only goes up by 4.
Ah, yes.
So you actually don't have as much strength to bear. This is, again, why grasshoppers can jump really high, and we struggle with this, and why ants have a lot more strength to weight ratio than humans. And so if you're thinking about how to move something, the inertia of the object that you're trying to move is proportional to the mass. If you're trying to rotate something, it's proportional to what's called the moment of inertia, which is mass times the distance away from center. And so again, your ability to move, say, a limb is scaling more slowly than the amount of force required to move that limb with the same degree of acceleration, or the same proportional acceleration. The other challenge is you have to, of course, move that limb farther, faster to make it look the same. So not only did it get heavier and you didn't get strong at the same rate that you gained mass as you grew, but you're also trying to move, say, your arm over a lot greater distance, which means you actually need an increased acceleration. And so that works against you as well.
And so you're in my mind, when I imagine a giant King Kong moving in what looks like slow motion, that's not just me kind of imagining that. That's actually what would have to be true if it was that big.
Yes. Yeah, exactly.
And actually, I mean, maybe an even more morbid way to look at that, based on what you just described, the multiples being what they are. King Kong being what? I mean, it's like a 10-story tall animal, so like 100 feet tall compared to like a 6 foot tall. That's more than 1 or 2 or 3 doublings.
Yeah.
You know, what is that, like 6 to 12? I mean, it's like 3 or 4 doublings. And so the mass, like the ratios just absolutely fall apart. The thing wouldn't even be able to stand up, probably.
Right. Yeah. And that's why we don't actually have like animals that walk the earth that are that large. You know, the largest modern living animals are probably elephants. You know, maybe the tallest would be giraffes, but in terms of like the most massive, I'm guessing are elephants.
Among the animals that have to hold themselves up.
Yeah. Yeah. So land, we'll call it land walking animals.
Yeah.
Yeah. Let's be specific. Because yeah, I think the largest animals I know of on the planet that are like a single organism would be blue whales. And of course, they're floating in water where they don't have to hold themselves up. The buoyancy helps. So yeah, as you scale up, your mass is going up, and and there's some technical terms for this, and they're a little bit annoying, but let's go through them.
Okay.
So the first, call it one-dimensional quantity of size, we called linear, and think of that like a line. Like a line measures between 2 points. You know, we're going to increase it and decrease it, and that's going to be our fundamental unit of scale here. The next quantity is the measurement of area. And this can be cross-sectional area or surface area. It really works the same for both. It's essentially length times width. So it's what we call squared,
Mm-hmm.
because if you're measuring the area of a square, you measure the length times the width, or the base times the height. And this means it's a value multiplied by itself. In math, we call these quadratic, which is a shame because quad means 4, but we actually mean it's to the power of 2 here, or to the second power here. And I assume that's because it's related to like quadrilaterals, maybe. We talk about
Yeah.
quadratic equations and quadratic formulas.
Yeah, I wonder if it could also be that the size of this dimension increases by a factor of 4
When you double it.
when you double the linear size.
Yeah, that may be. But yeah, the term quad gets applied a lot to the cross, like to perpendicular axes as well. So yeah, I'm not exactly sure
Mm.
why, but it's a little bit of a shame because the exponent is 2. You're taking it to the second power, but we call it quadratic.
Yeah. Yeah, it's weird.
And then if you're looking at a measure of volume or of as a result of mass, now this is length times width times height. And so that's a quantity raised to the third power, referred to sometimes as a cubic term in a function. And again, this is because it's how you would take the volume of a cube given the linear size length. So we talk about linear, quadratic, and cubic. That's the base value. And then quadratic is the base value times itself, or base value squared. And then cubic is the base value times itself, raised to the third power. And so with that in mind, then you can start to look at different types of different physical properties, and you can ask, is this a physical property that's associated with the length or the height, any linear dimension of the object? Is it associated with the cross-sectional or surface area of the object, in which case it's going to scale quadratically? Or is this associated with the volume of the object, in which case it's going to scale cubically? So as we talk about maybe a very large animal, again, volume and mass are scaling cubically. If it has a skeleton holding up its weight, well, how strong are the bones? The bones' strength is essentially associated with their cross-sectional area, and that's only scaling quadratically. So
Yes.
you double the size of the object of the animal, you again multiplied their mass by 8, but you only multiplied the strength of their bones by 4. So
Yeah, or they have to have thicker bones, I guess, because
yes. So that's exactly right. The result is they actually have thicker bones relative to their size.
even as a ratio, like even normalizing for their
Yep.
size.
Yep.
Like, so if you took a human being and made it 4 times the size, like let's go with simpler. If you took a human being and doubled its height,
Yeah, you made a giant. Yeah,
the bones would have to not just be double the thickness in order to support that weight, right?
that's right. Yeah, I think, and you could do the math, they'd have to be double times the square root of 2. So they're about triple the thickness.
Okay.
Now you just allocated more of the mass of that object to bone as opposed to circulatory tissue or muscle. So you start to play kind of like a losing game, where if you kept growing that animal in sort of this abstract model, you get to the point where it can only be made of bone if it's going to support its own weight. And there's no longer any mass budget for all the rest of the systems that make the animal function. And you've essentially created, an upper limit for how big you could make an animal based on that type of bone structure.
Yes, because the bones would. Yeah, that makes sense. You can't just be all bone. There's other functions needed.
Yeah, be a pretty uninteresting creature if it was just all bone.
Yeah, I mean, if eventually all things, when scaled up big enough, turn into rock.
That's
or
right.
else they can't support themselves.
Yeah, exactly.
Which is why I guess you can have a mountain, thousands of feet tall.
Yeah,
But you can't have an elephant that's thousands of feet tall, or else it turns into a mountain. So in other words, all animals are mountains in the limit.
that's right. Just in their own limit.
If you go far enough.
Yep. And then if you go in the other direction, as you scale down, then you can actually, you're reducing the linear size of an animal. So let's say you're making like a mouse or something much smaller. And even if you started with elephant shape, you would find as it got smaller, you could afford to further make the bones, say, even more slender, because they would have enough strength to support the remaining weight.
Mm-hmm.
And now you have the opportunity to put, say, more muscle or other systems that are useful onto that skeleton. As you've done this, given that even if you scaled kind of proportionally, because the strength, like I said before, the strength of the muscle is also proportional to the cross section, elephants don't jump very high because their strength to weight ratio is quite limited by both the required thickness of their bones, but also the fact that at their size, their muscles kind of barely have enough force available to move them, in a walking motion. I mean, and they can run, but they're not going to perform any high jumps like a grasshopper could. On the other extreme, and maybe we stick with mammals. You look at like a rabbit or a deer that can jump quite high. They have much skinnier bones. They also, their ratio of their muscle cross section to their total mass is much more favorable to that muscle. And then even other little things like their circulatory system can be much more efficient, like the distance from the heart to that tissue and the amount of blood flow and oxygen they can provide. It's a lot easier to deliver oxygen at that very small scale and even have that muscle run at a more efficient setting, essentially, making more like sprinting and jumping available as opposed to sort of lumbering, which seems like elephants' primary mode.
Which is probably how mice think of us.
Exactly.
Like
look at those lumbering beasts.
Yes, they're so slow.
Yeah. And then so all the way down to the extreme, like to an ant or something like that. And you think about, how many times you're sort of halving size as you go from, say, human scale down to ant scale.
Mm-hmm.
Each of those times, you are introducing an increase in strength to weight ratio. And so each of those, essentially, each time you cut the size in half, you have an opportunity to double the strength to weight ratio. And so by the time you've made something very small, you potentially have a very high strength to weight ratio, meaning you can carry something that's heavier than you are, or you can jump much higher than, your body height and so forth, which humans struggle to do.
Yeah. It's so cool.
So that's like scaling laws for animals.
Mm-hmm.
This shows up all kinds of other places too. So like Dave, you and I both have spent time building and flying RC models, remote control airplanes and gliders and so forth. And again, have you noticed there's a very distinct way that a model flies versus like its full scale counterpart? And like, what have you observed there?
Oh yeah. Like I can build for very inexpensively, I could build a model airplane. And when I say inexpensively, I mean compared to what a full-scale plane would cost, that can do things that are so high performance that no full-scale airplane could ever dream of it. For example, I could build a model airplane that I can just hold in my hand and point its nose straight up and then hit the throttle to full, and it will just jump out of my hand straight off the ground and just go unlimited vertically into the sky.
Yeah.
And there's no engine on Earth, no airplane on Earth that could do that at full scale.
Yeah, just take off like a helicopter, basically.
Yeah, exactly.
Yep. So why does that work at model scale as opposed to at full scale?
I haven't thought about this. Let's see. I mean, it's got to be, obviously, the power to weight ratio is a factor here.
Yep, so that's the first part.
Why? I don't quite understand why the power to weight ratio is so much higher in a small airplane.
Yeah, I think it comes back. There's a few different ways we could look at it. So if we look at power to weight ratio, we could look at engines, like gas engines and how they scale. But in your case, it's probably an electric motor. And thinking about an electric motor, again, mass is going to be kind of linear with volume, or cubic with volume. So we doubled kind of the size or linear dimension of an electric motor. We're going to 8x its weight. I'm suspecting that the amount of power that you can generate with an electric motor is going to be proportional to some area properties, like the area of the magnetic field it generates and the cross-sectional area of the wiring that you're flowing the current through.
Yes, because in order to have more energy flowing at a higher rate, which is the definition of more power, right? It needs somewhere to go.
Yep.
And that means wiring that is thicker, in other words, has less resistance in it and can accommodate more electrons moving.
Yeah, so I'm guessing, I haven't done the analysis myself, but I'm going to guess that it's something like that small electric motors can generate more power per unit of mass than large, again, due to these scaling factors. And then if you look at the airplane itself, the airframe is going to increase in mass cubically as it grows. And so a small airframe has an advantage there. And if you look at the propeller, like this is a propeller-driven airplane, let's say, the thrust available to the propeller is probably to a first order proportional to the surface area that it sweeps through, which is why helicopters have much bigger rotor blades than airplanes do. And so I'm guessing there's some scaling benefit there as well, that as you scale the airplane up, that the propeller's area, the amount of air it can interact with is only going up quadratically, even though its mass is going up cubically. And so I would guess that that's another challenge for at least propeller-based aircraft design. Not to mention, you need to deliver power to that propeller through a motor of some type, which is also limited. So those are just a couple thoughts. Another one that I've noticed when you're flying models is that like they turn way sharper, they roll way faster.
Yes.
Again, going back to that like small scale model versus large scale real thing. Like if you watch, I think when they did the first Boeing 747, like one of the early demonstration flights, and the test pilot rolled the plane, actually did like a full 360-degree barrel roll. Like it's like this slow lumbering roll that it's actually extremely hard to replicate with a model, because your models, the small scale models, just want to roll faster.
Yeah.
And again, they have lower mass. They have a much lower what's called moment of inertia. And just fundamentally, like their wingtips on a small model to go through a full 360-degree roll about its central axis, like they don't have to travel very far.
Yeah, the linear distance of the tip of the wing is not that long.
Yeah,
when it goes around the full circle. And
so
not to mention that the speeds. So I'm trying to think here. So there's only a certain amount of airflow passing over the wing, and it's ultimately the deflection of an aileron control surface on the wing against the incoming wind that's passing over it that is what generates the rolling force on the wing, right?
Yep.
And I think, okay, well, what speed is a Boeing 747 flying at? Well, it's probably like 400 to 600 miles per hour, somewhere in that range, right? Like at cruising speed?
Yeah, just below the speed of sound, 0.8 Mach.
Yeah, and then we've got our model airplanes that can be going as slow as like 20 or 30 miles an hour, but also as fast as like 60 or 80. So you could have 60 miles an hour of wind flowing over this tiny little surface, deflecting something that weighs like half a pound. But then you have something that weighs 1,000 times or 10,000 times more, but it's only deflecting wind that's moving 10 times faster.
Right. Yeah, and you have a very non-linear effect, we would say, at the speed of sound. So big objects run into certain other properties like that the small object isn't going to deal with. But yeah, that's another good point. When you look at an airplane, also, the amount of lift that its wings are generating is, other things being equal, is roughly proportional to the surface area of those wings. So again, that's a quadratic scaling property. But of course, the mass that those wings have to support is growing cubically. So again, you double the size of an airplane, and the wing loading, the amount of mass of airplane being held up by each, call it square inch of wing, is doubling every time you double the size of the airplane. So you get a much higher wing load. You're asking that wing to do more work, which means you need more airspeed for it to be successful. And same with those control surfaces. The control surface, the amount of, when it deflects, the amount of air it can deflect, and thus the amount of force it can impart onto the system, is going to be proportional to the amount of air that is interacting with, which is going to be somewhere between linear and quadratic times the airspeed. And again, that's going to be less than the increase in mass and the increase in moment of inertia, which is going to be cubic. So the result is, small scale models flip around a lot faster than the full size airplanes that they're replicating do.
And this also explains why we don't have gigantic airplanes. It's interesting because in the early history of aviation, I remember I've seen pictures of those airplanes, like these little passenger planes that carry maybe 20 people in them. And I think generationally, those things increased in size and passenger capacity a lot in the first decades of aviation. It was like, now we can carry how many people are on board like a typical commercial flight? It's in the hundreds, right? At least 100.
Yeah.
That's a lot of people, but it stopped there.
Yep.
And we're not now, like, no aviation company, Boeing, Airbus, they're not announcing plans for a 1,000 passenger airliner,
Yeah.
And this is why, because they're bumping up against these physical laws.
Yeah, if anything, they kind of scaled down just a little bit from probably what the biggest ones, the 747 and the Airbus A380. And some of that could be the way that human beings want to go different places on their own schedules, and just getting 1,000 people to all choose to go the same place at the same time isn't how our society works. But I also wonder if they hit some inefficiencies at those maximum scales and found they could actually build a better performing system, even when you consider that you have a fixed overhead of the whole airframe and the captain, crew, everybody on board to make the thing work. So you'd like to have as many passengers as possible, but if you just optimize purely for size, maybe they lost some other things in the process that they gained back by downsizing a little bit.
Yeah. And obviously economics are a huge component to all decisions that are made by these companies.
Yeah. But yeah, I suspect that if you said, I want to make an airplane that can carry twice as many people, that it gets a lot harder because, again, you're running into these scaling problems once again.
Exactly. Like the mass is going to have to be a lot bigger, obviously, like we talked about, even bigger than the ratios would, linear ratios would suggest. And then that means more propulsion, that means more fuel. And then I bet you it's a vicious cycle.
Yeah.
Where it's like, well, the fuel also has mass, and so we need more fuel to make the thing go, and we need more engines, and those are heavy. And it's just like, forget it. Let's go back down to the small size.
Exactly. Yeah, an extreme of that. And I was going to look it up before we talked, but I didn't. So we'll just have to wing it a little bit. An extreme example of that is in rocketry. And so have you ever built model rockets, Dave?
Oh, yeah, for sure.
Yeah. Mm-hmm. And like, what do those things look like as they come off the pad?
They jump off the pad at like this impossibly fast acceleration. It's almost like they popped off the pad.
Yeah, they're super hard to track with your eye. They just disappear like almost instantly.
Yes.
Then you go find them somewhere up in the sky, hopefully.
Yeah.
And again, that's because they're able to generate, in this case, a thrust to weight ratio just extremely high. So they get a huge amount of acceleration. And that's because they're very light. Like they take advantage of this downscaled property that you can make them out of often a thin walled cardboard tube. They weigh almost nothing.
Yeah.
The motor is relatively compact as a solid fuel motor, and the thrust that it generates is going to be proportional to the interior surface area of the burn chamber in the motor, which is quadratic scaling, and you've got cubic scaling of mass, which again, as you make things smaller, the mass is diminishing faster than the thrust is diminishing. So you end up with a high thrust to weight ratio. Take it to the other extreme. What does it look like to watch one of the modern, large scale, either satellite launch rockets or human carrying orbital rockets? When they lift off the pad, it's a very different experience.
I know, it almost looks like it's in slow motion.
Yeah. And I feel like watching some of the early ones, like the Saturn V's, like you wonder for a bit, like, are they actually going to go? Like they make a lot
I know.
a lot of mess,
Yes.
a lot of smoke, a lot of fire, a lot of noise. And that initial acceleration from 0 to something is pretty slow. And then of course, they continue to accelerate. And if anything, they'll actually increase their acceleration if they're not throttled over time, because as they burn fuel, they get lighter. And so they actually can increase their thrust to weight ratio as they climb.
By dumping weight.
Yeah, literally by burning it and dumping it.
Fuel that's not actively being burned is nothing but weight. It only slows you down.
Exactly. So yeah, there are equations for this, but if you want to double, say, the payload carrying ability of a rocket to a certain orbit, which means a certain height and velocity, you can't just double the rocket, because you end up doubling all the fuel as well. And again, your thrust is only, if you double the size of the rocket, your thrust is only going up at best quadratically, because it tends to be a function of area. Meanwhile, the mass went up cubically. So it's one of these like super painful laws of diminishing returns. Like to launch a little bit more payload, a little bit higher into orbit requires a lot more rocket, because the majority of the rocket's job is lifting the rocket itself, and only a little bit of its energy is left over for the payload itself.
Yeah, I mean, as a proportion, I actually haven't not seen these numbers, but do you happen to know off the top of your head, as a ratio of the weight of the payload to the weight of the fully fueled rocket, do you have any idea what that ratio is?
I don't. Man, that's a good question.
I'm guessing it's got to be like single-digit percent.
I bet it's lower than that. But yeah, I mean, it's going to be very small. I don't know. Does it take 100 pounds of rocket to lift 1 pound of payload? Maybe. Now you got me curious.
Okay, so according to a quick Google search, it looks like about 6% of total mass is payload.
Higher than I thought it would be. But yeah, still, compared to
But it'll get worse, right? Like the more payload, if you wanted to have double the kilograms in payload, that percentage is going to go down, I imagine.
Yeah, I think so. Unless you've created a system that you can sort of scale out linearly. Like when you attach more boosters, you might get some linear benefit from those. But if you're kind of like making like if you're using the same, yeah, maybe if you're able to add entire additional rockets. So you're adding more engines and you're adding more fuel. But if you sort of make it taller and just put more fuel into the same amount of engine, that's when you're really losing.
Yeah, and I guess this explains why we have seen rockets like that, where it's like multiple boosters strapped to a central booster.
Yep.
You know, the Space Shuttle did this. The SpaceX Super Heavy does this.
Yep. And then like the Starship, where they have more engines. So again, you're getting more thrust. You're getting like at least a proportional increase in thrust as you add those additional engines. You do have to provide fuel for all of them, but you might be able to scale out at least linearly in that way, as opposed to for each of those, you have to do some math and say, how much fuel should each engine be responsible for? Of course, it has to be more than zero because you want it to actually do some useful work, but you're getting diminishing returns as you add fuel that's going to flow through any given engine.
Yeah, yeah. Very interesting. So that whole system is probably a lot more complicated than the theory that we've just been talking about would predict. Like, it's not just about linear size to quadratic surface area to cubic.
Yeah.
Volume, right? There's other factors at play because not only is it that scaling, but it's also dynamic. Like you were saying before, as it lifts off, you're actually losing weight.
Right.
Which means your power to weight's improving.
Yep.
But, and of course, then the thing has to fly home as well, so it's like, it's so complicated.
Yeah. Yeah. So one way to think about that is if you didn't add engines, like, so you just stick with the same airframe and the same engine set, and you wanted to be able to have the final stage carry 1 more pound of fuel to get you however much higher or faster that's going to get you, you have to carry that additional pound of fuel all the way up to the top of the previous flight path, which means you had to have enough fuel to carry that 1 pound up there. And so that 1 pound turns into some multiple. But yeah, I haven't looked at the exact math on that. One other area I was thinking about this, I was talking with my son the other day, and he was talking about hailstones and like, why are hailstones the size they are? When you get a big storm that comes over and hail falls. Intuitively, we know that sort of larger size hail are associated with more severe storms. But have you ever thought about like what the limiting factors might be that would lead to the particular size of hail that comes out of a given storm?
What the limit is?
Yeah, or like what determines that? Like, why do you get pea-sized hail or golf ball sized or baseball size?
I have a guess. I would guess that baseball size is extremely rare. Okay, so hail grows the longer it spends flying around the atmosphere in a moisture-rich environment where water can condense and freeze on it.
That's right.
In other words, it's picking up ice layers the more it stays in the air. But at a certain point, no amount of naturally occurring wind can keep that thing flying up in the air because the wind, it's kind of circulating, I guess, in some pattern to keep it in the air longer.
Yeah.
And so because it gets too heavy because of scaling laws, like the cross-section that the wind is pushing against of the thing no longer is sufficient to generate enough friction to counteract the weight, which is now increasing at a higher rate than the cross-section is. And so at some point you cross over that equilibrium and then it just falls to the ground.
Yep. Yeah, I think that's it. So yeah, in a strong thunderstorm, you have massive updrafts, and it has to be cold enough up in that particular storm we're talking about to freeze that water vapor into ice. And I do think sometimes hail, I think I've read, they'll actually follow kind of a circulation pattern where they get in a strong updraft and they get boosted up high in the cloud. And then often near the top of the cloud, there might be like a wind shear where there's a horizontal component to the wind that blows to the side. And so sometimes they'll just get blown out of the storm and then they fall down.
Ah, yes.
Like on the leading edge of the storm, pretty commonly.
Yeah, sure.
But sometimes as they fall back down, they sort of recirculate and fall back into that updraft and they get boosted up again. And so they kind of circulate. And so if they don't get blown out of the updraft, but instead essentially fall through it, then that's going to happen when, as you said, when the force of gravity exceeds the wind resistance in that updraft. And the force of gravity on the hailstone is going to be proportional to its mass, which grows cubically with size. But the air resistance is going to be roughly proportional to that cross-sectional surface area, which grows quadratically. So I would guess that given a particular velocity of updraft, you could then compute, okay, here's the maximum sized hail that could be supported in this updraft. Larger will fall through to the ground. Smaller will actually continue to rise and be supported by that updraft until they accumulate enough of that frozen water onto them that they then fall through.
And that's a tipping point. And so I imagine that there's a limit to most wind speed in most storms. And, well, I guess let me put it this way. The more the updraft speed, the bigger the hailstones you're going to get. But there must be kind of like an asymptotic diameter of the hailstones, because at some point it's like there's no way you're ever going to get wind big enough to compensate for the bad ratios.
I think that this is probably why we don't experience, it's very rare to experience, you hear these extreme stories of softball size or maybe something bigger, but those are extremely rare. We don't hear about like car sized hail. Like that's not, I've never heard of that.
Thank goodness.
Yeah. We'd
be in a lot of trouble. We would have to live underground.
We'd have to build our cities differently. Yeah.
Yes.
And I suspect that goes back to if you look at the expected maximum sustained updraft wind speeds in storms on Earth, that they follow a kind of a natural range, a distribution over that range. But again, there are upper limits that are rarely exceeded.
Yeah, and imagine if you took the highest wind you've ever experienced on Earth and you doubled it. You're still not going to get hailstones that are, in terms of radius, double the otherwise big hailstones, right?
I think the math might say you would.
Well, because isn't it true that if you double the surface, well, let's see. If you've doubled, maybe. So if you've doubled the mass, that actually means proportionally you've increased the surface area less than double.
Well, let's double the diameter.
Okay.
Then we quadruple the surface area or the cross section.
Mm-hmm.
And we 8x multiply by 8 the mass.
Mm-hmm.
But that 8x mass divided by that quadrupled surface area is double. So the weight to surface area ratio has doubled, which if the wind resistance is linear in the wind speed, then doubling that would double the size of object it could support. I actually don't know if that's all linear, if those relationships are all linear, but that is how the proportions would work out. But how many times can you double the updraft speed of a storm and still find an example of it on Earth? It would be pretty rare.
Well, the limit's going to be the speed of sound, probably, right? Like wind. I don't know.
Yeah, can you imagine an updraft that was
1,000 miles an hour,
supersonic? That would be some storm.
I'm not even sure if that can naturally happen. I mean, because that means that the particles in the air are going to be pulling away from each other at a rate that, I don't know.
Yeah, I mean, we're in weird territory here. So I think that's unlikely to happen for many reasons. But the weird part would be if the air was moving faster than the speed of sound with reference to, say, the ground where we are, it doesn't require that there be any like air-to-air interactions where the shear rate is faster than the speed of sound, which is the problem that happens when like flying objects exceed the speed of sound, is the air around them is proportionally that much slower. Because you could sort of have like a gradient where you have slow-moving air at the outside and then faster and faster towards the core. So I suspect it's actually possible to create like a supersonic jet of air if you did it right. I don't know if there's any process out there that would do that, though. Maybe that's something to dream about in the future.
It'd have to be like electromagnetic or something to get them to move.
There you go. But maybe this is it. We make very fast-moving streams of air, and now our conventional airplanes can go much faster through them, and we'll have solved like supersonic transport in a new way.
Well, I was just thinking we could make Volkswagen-sized hailstones, which would also be fun.
And transport them supersonically. Yeah. So it all comes back to the same thing. Get in this bus, and you're going to be in Europe in 2 hours. Oh, man. Okay, well, any other observable outcomes of these scaling laws that you want to talk about, Dave?
Yeah, there is one other one, and that is gas mileage.
Ooh, okay.
So, like when I drive my car, so I drive an electric car and I also have a gas car. Mm-hmm. And having an electric car has made me very sensitive to my speed, as it influences my efficiency of basically the distance I can travel due to the energy that gets drained from my battery.
Yeah.
And it's made me more sensitive to this. And the other thing that's made me more sensitive to this is riding my bike in big groups of road cyclists.
Okay.
And that is the really impactful effect of wind resistance on anything traveling. And there's a scaling law there because basically as you increase your speed, the amount of force that the wind is pushing back on you does not increase linearly with your speed. It increases as a square of your speed.
Okay.
And so the amount of effort that you have to put into your pedals to add an incremental 1 mile an hour to your speed increases for each mile an hour you add to your speed.
That's true. Yeah.
So the effort to do, like, say, 20 miles an hour, you might think, oh, well, I'm just going to add another 25% of effort to get up to 25 miles an hour. But that is not at all the case.
Yeah.
I don't know I can't do the math in my head or in public at the moment, but the effort to go from 20 to 25 feels like almost double.
Right. Yeah, and if it's quadratic, the doubling in effort would be required to go 1.4 times the speed, or roughly the square root of 2.
So a 40% increase takes 2x the effort.
Yeah.
That's what you're saying.
And to go from 10 to 20, doubling the speed would take 4 times the effort.
Yes. And so what road bikers do to compensate for this is when you ride in groups, you can actually take advantage of these physics and kind of do a cheat code, which is called drafting.
Oh, yes.
And this is where you have at least two cyclists, and one of them takes a turn riding in the front, and the other one rides their bike directly behind. And it's like, we're talking like 6 to 12 inches between your wheels.
Yeah.
And if you can nestle into that little pocket of air, the air has been dispersed by the person in front of you, and so you're not fully confronting the air resistance, and instead you're like swimming in this eddy. And so now the resistance is greatly reduced. And so what you do is you take turns being on the front.
Yeah, because the effort in the front is much higher, isn't it?
Exactly. So if you're doing 20 miles an hour in the front, it's going to feel like one effort. But just anecdotally, when I'm in the back position, that 20 feels like the equivalent of 15.
Yeah.
Thanks to the laws, the square root, or the square that we were just talking about, that is substantially less exertion on my part, even though it's only 25% less speed.
Yep.
So this works best at higher speed. So the faster you're going, the more it works. And the more air that front rider can displace, the better it works. So if you have someone who's a lot shorter than you and a lot skinnier than you, it doesn't work that great. But if you have a big, tall, thick rider in the front, or even better, two riders in front of you, and you're kind of behind and between them, it is just like paradise.
Yeah, like you're hiding your Volkswagen behind the semi-truck on the freeway.
Yes. In fact, just as an interesting anecdote, so I have a friend who, we did a 50-mile ride a couple of years ago, and we had stopped at a gas station to get something to drink, and he saw a dump truck riding by. And dump trucks accelerate very slowly. It came to a stop in front of the gas station, and it was obviously continuing straight, and there was no other intersections or anything. So he jumped on his bike and just ditched us and got in behind that dump truck. Yeah. And before we knew it, he was doing like 30 plus miles an hour on his bike, just like maybe like 2 feet behind that dump truck. And we're like, you are going to get killed, first of all, but second of all, awesome. Like,
yeah,
so
totally.
Cool.
That is awesome.
He did that for a couple of miles, and then we eventually he fell off somehow. Like when I say fell off, I don't mean crashed, but he was unable to sustain it, and then we caught up to him, but
couldn't stay in that wind shadow.
Exactly.
So yeah, I mean, whether it's the dump truck or the biker in front of you, you've created, I mean, they're dragging along that jet of air we were just talking about, not supersonic, but definitely reducing the air resistance. So there's a couple things there. I don't road bike, I do mountain bike, and you feel the wind there, but I have a similar experience to what you described. Years and years ago, my sister and I entered an inline skating marathon. So we were wearing our rollerblades. We both had kind of hockey style rollerblades, not like the super speedy ones, but just recreational. And we entered this marathon, and there's a professional group up at the front. Like there's a professional everything, I guess. But that group of people, of course, they had these very high efficiency skates that resembled like speed skates from ice. Like really long, lots of wheels. They had like 5 wheels long at the bottom and kind of a softer boot that's more flexible than like a hockey skate. And they're all wearing speed suits, tight fitting clothes to reduce that air resistance. But what we noticed was they did that same thing. They all got in a line, and they would literally place a hand on the person in front of them, like on the small of their back. And then they would stride in unison. And so they maintained this very close together, like a caterpillar, basically cruising. And so that, they're quite fast. And so my sister and I tried this, just the two of us, because we were skating this together. And the person that's behind could actually push the front person. So you could actually kind of like go faster.
Without touching them, you mean?
No, in this case, we're actually touching. Like you put your hand on their back and actually push. So on the bike, yeah, you're just kind of enjoying the benefit of the person in front of you pulling you along with their wind shadow. But on skates, you could actually contribute to the net velocity of the group by pushing a little bit from behind.
Wow.
We took turns, but we could actually go faster than either of us could have sustained as the front skater as well by getting like a little bit of help from behind. And so, yeah, it was quite remarkable. I mean, it was fun. We got to hang out for the whole race, but also like both of us finished faster than we could have as individuals.
Yeah, that's so cool. I love that.
And then one other thing that I realized when you were describing that, and I remember hearing this, that air resistance, wind resistance is like it increases, disproportionately to your velocity. And I've heard quadratic mentioned as well. I'm actually not sure why, but it's observable. It's there. And B, that actually means that if you were to double the wind speed, you actually could probably hoist much larger hailstones because you're actually increasing the wind resistance they're encountering for what it's worth.
That is a good point. Okay. I think Volkswagen-sized hailstones are a possibility, and we should pursue that.
We should definitely pursue that. That sounds like exactly what humanity needs from us.
There are other factors at play, of course, and you touched on a few of them, and I actually pulled up the wind resistance formula while you were talking, but
the
coefficient of drag, of course, is a big factor, and that has to do with the shape and smoothness of the object. Teardrops have a lower coefficient of drag, teardrop-shaped items, compared to like a block. Air density has an influence on it, linear. The denser the air. Of course, the variability in the air density that humans tend to experience is pretty small, a small range. And then, of course, you mentioned cross-sectional area. That is a linear factor, and as you mentioned, and then velocity is a square factor. So
crazy.
And then all of that is multiplied by 0.5 for reasons that I wonder if someone knows.
Yeah, just because. This is what happens when you build formulas based on observation.
Yeah. Interesting, right? Like, yeah.
I'd have to look and see why. Because why would you not just make the coefficient of drag be half what it is and then get rid of that?
Yeah, that's a good point.
It probably came from some other good reason. They're like, oh, this is the right property here. And it turns out you need half of it over here for this other thing to work out.
Well, one half times a coefficient times a variable squared looks a lot like a derivative or an integral.
Yeah.
So
yeah, exactly.
There's probably something there.
It looks like a common. Yeah, that's a fair point. Nice. I have one other thing to mention. I guess I was thinking about scaling. We talked a lot about solid objects. In fact, it's funny because we started by saying, let's talk about a hollow object. And then we spent the whole time talking about solid objects.
Yeah.
What happens with hollow objects is kind of interesting. You think about like containers, and maybe an interesting example is like a cardboard box that seems like the world's commerce travels around in these days, at least for the last mile. And think about some of the properties of those. This is one where scaling can help you. So if you double the size of a container, you are going to get 8 times the capacity, or you double the size of a bucket. It's going to hold 8 times as much stuff inside. And so as long as it's strong enough, then the amount of material you used is going to quadruple, but you're carrying 8 times the amount of volume inside it. So you've actually used half as much packaging relative to the mass of what you're shipping if you double the size of the container and you keep the same wall thickness, for example. So this is, again, why sometimes, and similarly then, if you're looking at, well, how much shelf space does it occupy? Well, that's linear as long as height and depth aren't a restriction. If you have kind of a fixed size shelf that it'll fit into. And of course, how many handling operations does it require? How many times does someone have to pick it up, put it down, scan it, and so forth? That's actually singular.
Yeah.
So there is an incentive to make bigger containers as long as your infrastructure can support them, you have enough stuff to send that way, and they're still strong enough to do so.
Strength and the logistics of moving them around is probably a constraining factor there. And if I had to pick and just guess what the sweet spot is for that optimization curve, it's probably going to look a lot like the shipping containers that they put on cargo ships.
Right. Yeah. That's probably our current humanity scaled stuff movement quantum. Yeah, that's a good point. And if you look at them, yeah, they chose steel instead of cardboard,
Yeah.
but they're kind of corrugated.
They are corrugated, yes.
Yeah. And rectangular cross sections stacked nicely. And again, they fit onto a semi truck, but so there's existing infrastructure reasons for why they're the size they are. But yeah, you'd have to change the design if you were going to say double them in size again.
And interestingly, like a lot of that can be traced back to non-physical law things, but I wonder if underneath they really are. So for example, you mentioned the semi-truck, which is limited in width by current road lane widths. And those roads were probably originated from the width of a couple of horses pulling a carriage behind them, and the width of those two horses was governed by the mammal scaling laws that we talked about earlier. And there's probably a power to weight ratio that's optimal for pulling around human cargo or human desired cargo behind two horses, Of course they can do more than two, but usually not two. There's probably other reasons why two works better than three side by side.
Yeah. There's a natural stability to two as opposed to other numbers.
Yeah, the derivative effects of motion kind of mess things up, I bet.
And I think you could trace, I'm trying to think, I think one of the input, like if you were going to tweak like a single parameter and watch the entirety of the Earth system come out differently, if you were to change the mass of the Earth, which would then have a proportional change in the gravity that we experience on the surface of the Earth, because that's proportional to the Earth's mass, I think it would change the sweet spots for all of these things in terms of size of animals and so forth, which would then change the sweet spots for the size of things that we built.
Yes.
And even the size of human beings themselves, I would guess.
That's what I was thinking too, yeah. And that there's a lot of usability changes that would probably have caused as well.
Yeah, if we had grown up on Mars or some planet that's smaller and had lower gravity, I would guess we would, everything would look different, but I think the natural sizes of things would be different as well. Or if we all grew up on a larger, more massive planet, which had more gravity, go the other direction. I suspect the lower gravity might favor larger objects and the higher gravity might favor smaller objects, just based on the way the scaling works out.
Interesting. But the laws themselves don't change. It's still the case, no matter what gravity you're in, that if you increase the size dimension of a cube of one side, then all the other ratios still happen the same.
Exactly. Yeah, because it's all relative.
And so what that means is there's probably a limit on the maximum size of mammals under different gravitational constraints. Because some of I'm not 100% sure on this, and so I'll admit that up front, but I think some of the body's important systems like blood flow actually take advantage of siphoning effects. Trees, for example, have something with that, where turgor pressure and other things like there is a maximum height that they cannot exceed because water can't flow up there in the same way that a siphon can't go over a certain height.
Yeah, especially if you're having to call it the pressure over the full distance. If you're able to take advantage of something like capillary action, you might be able to overcome. So another caveat in all of this is it tends to be most true in sort of these mid scales that we experience as humans. You get to really small things, then other properties take over, like surface tension and intermolecular interactions. And you get really big and other things take over, like the speed of sound and so forth. So it's kind of the sweet spot range where these various relationships, I'll say, hold. But yeah, that's a good point. On a different planet with distinctly different gravity, you might have much taller trees or much shorter, depending on how it went.
All right. Well, we had some explaining to do. Did we do all the explaining we came to do?
I think we did.
All right.
Yeah.
Well, thanks, Shane. I really enjoyed this.
Same here, Dave. Good to talk as always.